Today we will see next topic in our unit, that is sequences. Okay. So the new topic is monotone sequences. Okay. So monotone sequence is nothing but a sequences which are increasing or decreasing. Okay. So suppose we can see a sequence. Let sequence S is equal to sequences of natural numbers. So n term of the sequence is n. Now see, what is the first term of the sequence? First we can list the element of the sequence. So first term of the sequence is 1, second 2, third 3, 4 2, so on. So see, first term is 1, second term is 2. Second term is greater than or equal to first term. Here it is strictly increasing. Okay. Third term is greater than second term. Fourth term is greater than third term. So such type of sequences are called monotonic increasing sequences. Okay. Each next term is greater than its previous terms. Okay. Now we can see another sequence P whose n term is 1 by n. Okay. So what are the elements of this sequence? First element of the sequence is put n is equal to 1. So 1 by 1 is 1. Put n is equal to 1 by 2, 1 by 3, 1 by 4 up to so. See, first term was 1, second term is 1 by 2, third term is 1 by 3, fourth term is 1 by 4 and so on. First term is 1, second term is 1 by 2, second term is less than first term, third term is 1 by 3, which is less than second term 1 by 2, fourth term is 1 by 4, which is less than 1 by 3. This is the moderate decreasing sequence. Okay. So we can write definition of the monotonic sequences. Okay. So if Sn is less equal Sn plus 1, if Sn is a sequence, Sn is n term such that each n plus 1 term is greater equal n term, that is next term is always greater equal previous terms, then sequence is called monotonic increasing. If there is no less equal, or we can, if this is monotonically increasing, we can write this as if Sn is strictly less than Sn plus 1. Okay, this is valid for all n. This is also valid for all values of the sequence, all terms of the sequence. If Sn is less equal Sn plus 1, then we say that sequence is monotonic increasing. And here, if each term is strictly greater than its previous term, then we say that the sequence is strictly monotonic increasing. Okay, and notation is like this: sequence Sn is monotonic increasing. Okay? So, if this relation is valid, the sequence is said to be monotonic increasing. This or this. Here, we say sequence is strictly increasing. Okay, each term is strictly greater than previous term. Here, each term is greater equal its previous. So monotonic increasing sequence. Okay. Monotonic increasing sequence. Now what about monotonic decreasing sequence? Okay. This relation is for monotonic increasing sequence. Now its reverse, if each previous term is greater than its next term, like this. The term first is greater than the second term. That is, the previous term is greater than its next term. So we say that the sequence is moderate decreasing. This is valid for each term. Okay. So if Sn is greater equal Sn plus 1, that is previous term is greater equal upcoming term, and for all n, then sequence is monotonic decreasing. Okay, so monotonic decreasing, or you can say like this, that if Sn is strictly greater than Sn plus 1, each term, each previous term is greater than its subsequent term, strictly greater than, then we say that the sequence is strictly monotonic decreasing. Okay, and this must be valid for all. Okay. So just the idea of monotonic sequence is that sequence is either increasing or decreasing. Okay, But see, if I write the terms like 1, 2, 3, 0, 1, then again 2, then 3, then again 0. Okay. Now see, we can say this pattern is continued. Now first term is less than second term is less than third term, but fourth term is not greater than third term. Okay. This sequence neither increasing or decreasing. Okay. If sequence is increasing or decreasing, the pattern is valid, must be valid for each term. Here up to third term pattern is valid. The third term is greater than second term is greater than first term, but fourth term is not greater than third term. So the sequence is not monotone. Okay. For sequence to be monotone increasing or decreasing, these patterns must be valid for each and every term. Okay. So the definition of monotone sequence is a sequence which is either increasing or decreasing is called monotone sequences. Okay. Now we will see some examples. Okay. We will investigate whether this sequence are monotone sequences or not. So first example is sequence of squares of natural numbers. Okay. N term is n square. So element of this sequence are what? 1 square. So 2 square 4. 1 square is 1. 3 square is 9. Up to so on. Now see, each term, each next term is greater than its previous term. So the sequence is monotonely increasing. Or we can say here Sn is equal to n square and Sn plus 1 is equal to n plus 1 square. Now from our observation, if you put any value here and any value here it is n square, it is n plus 1 square. So n plus 1 square for any natural number is always greater than the n square for where n is a natural number. You put n is equal to 2 suppose. So 2 plus 1 is 3. 3 square is 9. N is equal to 2 square is 4. So 4 is less than 9. So just by observation you can see this sequence is monotony increasing because here Sn is less than Sn plus 1 for all values of natural numbers. So this sequence is strictly increasing, that is it is a monotonic increasing sequence. So now in this sequence we can write the element of this sequence which are the element like 1 upon 2 into 1 plus 1, so 1 by 3, 1 by 5, 1 by 7 up to so on. Okay. Now see, here denominator goes on increasing, so elements are goes on decreasing. First element of the sequence is 1. Second is put n is equal to 1, 2 into 1 plus 1, so 3, then 5, so around 1 by 5, 1 by 7 up to so on. The first term is 1, second term is 1 by 3. So first term is bigger than second term. Now second term is 1 by 3, third term is 1 by 5. So second term is greater than 1 by 5. So elements are goes on decreasing. Okay, so here Sn is greater than Sn plus 1. Okay, so previous term is greater than next term. So this sequence is monotonally decreasing. Okay, so this sequence is monotonally increasing. This is decreasing. Okay, now see this sequence. Minus 1 is to power n into n. This is the n term of this sequence. We know the element of the sequence. Put n is equal to 1. So we will get minus 1 is to power 1 into 1. So minus 1. The minus 1 square of minus 1 into then put n is equal to 2. So square of minus 1 into 2. So plus 2. Then minus 3. Then plus 4 up to so on. Now there is no any pattern here. See. First element was minus 1, second is plus 2, so second is greater than first. Now third element is minus 3, which is less than second term. Again, fourth term is greater than third term. So there is no pattern like the relation, like either sequence goes on increasing or decreasing. So again, see, here second term is greater than first term, but there is third term which is less than second term. So there is no pattern like Sn is less than Sn plus 1 or Sn greater than Sn plus 1, which is valid for all n. Okay. Sequence is neither goes on increasing, neither decreasing. Okay. So this is not a monotone sequence. For monotone sequence, we have to find some pattern which is true for, which must be true for each value of n. Here see, second value is greater than first value, but again there is third value which is less than second value. So there is no relation, such a relation here. So this sequence is neither monotone increasing, neither monotone decreasing. So next sequence, the constant sequence 1. The element of the sequence are 1, 1, 1 up to so on. Now see, second element is greater than first element, 1 is greater than 1. Again, third element is 1, which is also greater than 1. Okay, so we can say this sequence is monotone increasing. But we can also say this first term 1 is less equal 1, the second term 1 is less equal 1. So we can also say this sequence is monotone decreasing. So each constant sequence has a dual character. We can say it is monotone increasing or monotone decreasing because it is satisfied both relations. Sn is less equal Sn plus 1 for all n, and also Sn is greater equal Sn plus 1 for all. We can say 1 is greater equal 1, the third term is greater equal 1 up to so on, or this 1 is less equal this 1, this 1 is less equal this 1. Okay, so this sequence is both monotone increasing and decreasing. Okay, only constant sequence has dual character. Okay, now next sequence, first term is 1, second term is 2, third term is 2, then 4, again 4, then 5, again 5 up to so on. See, second term is greater than first term, third term is 2, which is greater equal second term, which is also 2. Then fourth term is 4, which is greater equal to fifth term also 4, which is greater equal 4. So this sequence is monotone increasing. Okay, but not strictly increasing. It's just increasing because third term is greater equal second term. Third term is not strictly greater than second term. Third term is just greater equal second term. This is also monotone increasing sequence. So this is monotone increasing. For constant sequence has dual character, it is either monotone increasing or we can say it is decreasing. This is neither monotone increasing, neither monotone decreasing. Now you will see a famous theorem which is known as monotone convergence theorem. Okay, so this theorem says that if sequence is monotone, okay, so either it is monotone increasing or decreasing. Okay, so if sequence is monotone and bounded, then sequence is convergence. Okay, so monotone sequence of real numbers is convergent if only it is bounded. Okay, this is one criteria for sequence to be convergent. Okay, so if the sequence is monotone, then it is convergent if only it is bounded. So in simple we can say a monotone sequence which is bounded always convergent. Okay, so we will see the proof of this theorem. Okay. Now we have already seen one theorem which says if a sequence is convergent, then it is bounded. Okay, so one part we have already seen of this theorem. What is the part that we know? Every convergent sequence of real numbers is bounded. We have seen this theorem. Okay, so we have only done with half part of this theorem. Okay, if sequence is convergent, okay, if sequence is convergent, it is bounded. Okay, now what will prove? Now we will prove if sequence is monotone and bounded, then it is convergent. Okay, so let Sn be a monotone sequence which is bounded. Okay, so Sn is a sequence which is monotone and is a bounded. So since sequence is bounded, it has least upper bound and greatest lower bound. So let this K, capital K, be the least upper bound of the range set of sequence. Okay, least upper bound of the sequence. Okay, This is the set of all elements of the sequence, that is range set of the sequence. Since sequence is bounded, this range set as a least upper bound. Okay. So as it is monotone sequence which is bounded, and since it is bounded, it has a least upper bound. Okay. So each element of the sequence is less equal this number k, since k is the least upper bound. Okay. Now our sequence is okay. So one more point here, that since we know what is least upper bound, we have seen if k is the least upper bound, no number less than k is the upper bound. Okay, since least, it is the smallest upper bound, so there is no other element which is less than k and still upper bound for the sequences. This is the least upper bound. Okay, so any upper bound is greater than k. There is no upper bound which is less than k. Okay, so if we subtract some very small number epsilon from k, then this is not the upper bound. Okay, since k is the least upper bound, smallest upper bound, so any number less than k, so k minus epsilon cannot be upper bound. So we can find number which is, we can find the element of the sequence which is greater than this number. Okay, so since k is the least upper bound, k minus epsilon, where epsilon is greater than 0, small number, then k minus epsilon cannot be upper bound. Since it is not upper bound of sequence, we can find the element of sequence which is greater than this k minus epsilon. So there is some natural number, say m, such that k minus epsilon is less than the element Sm. Sm is the some element of this sequence, where m is a natural number. Now here we are seeing sequence in monotone. So we can take two cases, either sequence is monotonic increasing or monotonic decreasing. So we will see first case where sequence is monotonic. So sequence Sn is monotonic increasing. Okay. Now sequence Sn is monotonic increasing. Okay. So what is monotonic increasing sequence? Monotonic increasing sequence, nothing but the next term of the sequence is greater than its previous term, and this happens for every term. Okay, that is Sn is less than Sm plus 1. Okay, now Sm is one of the element of this sequence. So if we take a natural number greater than m, we will get higher term of the sequence. Okay, so we can find a number, okay, such that now, so we have taken a monotonic increasing sequence. Okay, so for this Sm, if we increase the value of m, we will get higher value of the sequence. Okay, so since sequence is monotonic increasing, we have Sm less than some another element of the sequence, because we can find number element which is greater than this. So if we increase the value of natural number, we take value greater than m, we will get the value of the sequence greater than Sm. So there exists a, say, natural number m such that Sm is less than Sm. Why? Because sequence is monotonic increasing, and each element of the sequence is less than this least upper bound. Okay, and Sn is always less than k. Okay, because k is the least upper bound of the sequence. So each element of the sequence is less equal this element, because it is the upper bound. Okay, so less equal. Now see, from this and this, we can write one inequality, that is k minus epsilon, and this is happening for some n greater equal m. Okay, why? Whenever n greater equal m, then only Sn can be greater than Sm. This is our definition of monotone sequence. We know for monotone sequence, monotone increasing sequence, Sn is less than or less equal to Sm plus 1. Okay? So when we increase the value of a natural number, we get higher value of element of sequence. So whenever n is greater or equal to m, okay, whenever n is greater or equal to m, or Sn will be greater than Sm. This is the monotonic increasing sequence. Okay, if you increase the value of this natural number, you will get higher element of the sequence. Whenever n greater or equal to m, Sn greater or equal to Sm. This is by definition of monotonic increasing sequence. So we get k minus epsilon is less than Sm, Sm is less equal Sn, Sn is less equal k, so we can write Sn is less than so k plus epsilon. This implies Sn is greater or equal, this implies k minus epsilon is less than Sn, Sn is greater than k minus epsilon, and Sn is less than k plus epsilon. Okay, for all n greater or equal m. This implies for some epsilon greater than 0, we can find natural number m such that whenever n greater or equal to m, from this we can write, so for our simplicity we can write one more step here. Okay, so transfer this k to this side. Okay, so what will we get? So this implies Sn minus k mod, or this Sn minus k greater than minus epsilon, so k here get minus sign, this is less than epsilon for all n greater or equal to m. That is mod of Sn minus k less than epsilon. Okay, what is this? Then what mod of this number is less than epsilon? This is nothing but this, because we can write this as a, so whenever mod of Sn minus k is less than epsilon, we can write this as minus epsilon less than Sn minus k is less than epsilon. This is happening for all n greater or equal to m. Now see, for any epsilon greater than 0, we can find natural number m such that whenever n greater or equal to m, distance between Sn and k, that is mod of Sn minus k less than epsilon. What is this? This is the derivation of convergence of limit, and this implies the sequence has a limit which is k, that is sequence is convergent. So by definition of limit of sequence, this sequence Sn is convergent and converges to k, that is least upper bound. Sequence Sn converges to k, that is sequence Sn is convergent. Okay, so every sequence which is bounded and monotonic increasing, it is convergent. Now we will see second case. So only we take sequence Sn as a monotonic decreasing sequence. Okay, then we will again prove sequence is convergent. Okay, so now we have seen case 1, in which we have proved that if sequence is monotonic increasing and bounded above or bounded, then sequence is convergent. Okay, then now the case 2, we will take a sequence monotonic decreasing and bounded. Okay, now since we have proved case 1, we will use that to prove become very simple. Okay, so we have given Sn is monotonic decreasing sequence. Okay, now we will construct a new sequence Tn which is equal to just minus of the sequence Sn. Okay, so we have defined new sequence which is just minus of given sequence. Now since Sn was monotonic decreasing, and this is nothing but just negative of all terms, this is just negative of the given sequence, this sequence is monotonic increasing. See, given sequence Sn is monotonic decreasing, Tn is a sequence which is negative of this sequence, so this is monotonic increasing. Okay, so Sn is monotonic decreasing, Tn being negative of Sn, it is monotonic increasing. So define a new sequence which is negative of Sn is monotone increasing. Why? Because it's just negative of given sequence. Since given sequence is decreasing and this is negative of this sequence is increasing. Okay. Now Tn is increasing. Also Sn is bounded, already given. Okay, Sn is monotone decreasing and it is bounded also. Okay, we have already seen in statement of our theorem. This Sn is bounded. What is Tn? Just negative of Sn. So Sn being bounded, Tn also bounded. Tn is bounded also. Since Sn is bounded and Tn is just negative of this Sn, so Tn also bounded. Now sorry, Tn is monotonic increasing and bounded. So by case 1 of this proof, so by case 1, Tn is convergent. Okay. What is case 1? A sequence which is monotonic increasing and bounded is convergent. Okay. So here Tn is increasing and bounded, so it is convergent. And say limit is some value k. Okay. And say limit of Tn is equal to some element. Okay. What is our aim? Our aim is to prove Sn is convergent. That is, we have to find limit of Sn. Now, limit of Tn, sequence Tn. Okay, so we will write like Tn only. So limit of Tn is equal to, to provide simplicity, we maintain the notation. So limit of Tn is equal to limit. What was Tn? Minus of Sn. Limit of minus Sn. But we know limit of minus of sequence is equal to minus of limit of sequence. Okay. So this implies limit of Tn is equal to minus of limit of Sn. What is the limit of Tn? K. This implies this K is equal to minus of limit of this sequence Sn. Transfer this side minus to this, multiply both sides by minus. So we get limit of Sn. Okay. So this become minus K. So minus K is equal to limit of Sn. That is, sequence Sn is also convergent and converges to minus of K. That is, sequence Sn converges to minus of K. So this implies sequence Sn is convergent. Since sequence has a limit, sequence is convergent. Okay. So we have to second this also, which implies if sequence is monotone decreasing and bounded, then sequence is convergent. So what we have learned? So we learn if there is sequence which is monotone, so either increasing or decreasing, but monotone, and it is bounded, then sequence is convergent. Moreover, if sequence is monotonic increasing and bounded, then bounded above, then it converges to its upper bound, least upper bound. And if sequence is monotone decreasing and bounded with bounded below, then sequence is convergent and converges to its greatest lower bound. This is the one very important criteria of convergent sequence. So in simple we can write every monotone convergent sequence is bounded. Sequence which is monotone plus bounded is convergent. And if sequence is monotonic increasing and bounded, then it converges to its least upper bound. If sequence is monotonic decreasing and bounded, then it converges to its greatest lower bound. Okay. Now we will see example based on the theorem you have just learned. What was the theorem? If the sequence is monotone and bounded, then sequence is convergent. Okay. So example is to prove that sequence given by n term, this is the n term of the sequence, is convergent. Okay. So now we will try to use the theorem we have just learned. Okay. That is monotone convergence theorem. So we will first see whether the sequence is increasing or decreasing. Okay. For that purpose, we will take difference between n term and n plus 1 term. If difference is positive, that is, if Sn plus 1 minus Sn is positive, then sequence is monotonic increasing. And if Sn plus 1 minus Sn is negative, then sequence is monotonic decreasing. Okay. And if this much value for each n. So this is Sn. Then what will be Sn plus 1? Sn plus 1 will be 1 upon 1 factorial, 1 upon 2 factorial, plus up to 1 upon n factorial plus 1 upon n plus 1 factorial. See, this is Sn, this will be Sn plus 1. So see, in Sn and Sn plus 1, what is the difference? Difference is just in Sn plus 1, this term is extra. Up to this is same as Sn. Okay. So we take difference between Sn plus 1 and Sn. So this term get cancelled, only remain this. So 1 upon n plus 1 factorial. Now n is natural number, so positive. N plus 1 factorial is a again positive number. 1 upon positive number is positive, so this is positive. Okay. So difference between Sn plus 1 and Sn is positive. So this implies sequence Sn is monotonic increasing. Okay. Sequence Sn is monotonic. So we can write this arrow or just write monotone increasing sequence. Okay. Why? Because difference between n plus 1 term and n term is always greater than 0. And this is valid for any value of n. Okay. So this sequence whose n term is this is monotonic increasing. Now our next aim is to show that sequence is bounded. Okay. Sequence whose n term is this is bounded. Now what is the first term of the sequence? First term of the sequence will be just 1 upon 1 factorial, that is just 1. What will be the second sequence of the sequence? Second element of the sequence? Second element will be 1 upon 1 factorial plus 1 upon 2 factorial. That is 1 plus 1 by 2 factorial, which is also positive. What is the third element? Third element will be like this up to this. What is the n element? Sum of these terms. What is the n plus 1 element? Sum of this term. So each terms of the sequence is always positive, greater than 0. So sequence is bounded below. So by observation, Sn is greater than 0 for all n. Okay. So each term is greater than 0. So sequence is bounded below because each term is greater than 0. There is no term which is less than 0 of the sequence. So sequence is bounded below by 0. Now we have to find the upper bound of the sequence. So if we get upper bound, the sequence is bounded below, bounded above. So sequence is, we can say sequence is bounded. So we will find the upper bound of the sequence. If we get, the sequence is convergent. Why? Because in that case, sequence is monotone increasing plus bounded. So by monotone convergence theorem, sequence will be convergent. Okay. So this is our Sn. Okay. Now you have to note one inequality, that is 1 upon n factorial is always less than 1 upon 2 raised to power n minus 1, and this is true for each n. You can verify by putting the value of n. 1 upon n factorial always less than 1 upon 2 raised to power n minus 1. Okay. So we will verify this for two values of n. If n is equal to 1, so 1 by 1 is, what is this? So 1 upon 2 raised to power 1 minus 1. 1 minus 1 0. 1 upon 2 raised to power 0 is 1. Okay. Then so we can write this less equal. Okay. So if we put n is equal to 2, so 1 upon 2 factorial is 1 by 2, and 2 raised to power 2 minus 1. 2 minus 1 is 1, so 1 by 2. Okay. If you put n is equal to 3, then this becomes 1 upon 3 factorial. But 1 upon 3 factorial is nothing but 6. 1 by 6. 3 factorial is equal to 6. 3 into 2 into 1. And here 1 upon 2 raised to power 3 minus 1. 3 minus 1 is 2. 1 upon 2 raised to power 2. So 1 by 4. So which is greater? Here 6 is in the denominator, here 4 is in the denominator. Denominator is less here. This is less. So 1 upon a factorial always less equal 1 upon 2 raised to power n. So we are just verifying using 2 theorem. Actually this is true. This is the standard inequality. This is true for all the values of n. Okay. So we will use this criterion here. Okay. So this is our Sn. So Sn is, so we can write Sn is equal to 1 upon 1 factorial plus 1 upon 2 factorial up to 1 upon n factorial. Okay. But 1 upon 1 factorial, using this is less equal, put n is equal to 1 here, n is equal to n here, we will get here 1 only. This is less than 1 plus 1 upon 2 factorial. So 1 upon 2 factorial. So here 1 by 2 is less equal 2 raised to power 2 minus 1. 2 minus 1 is 1. So 1 upon 2 raised to power 1. So 1 by 2 plus 1 by 2. Then 1 by 3 factorial. Okay? Here 1 by 3 factorial. 1 by 3 factorial is less than 1 by 4. That is we can write as 1 upon 2 raised to power 2. So 1 upon 3 factorial is less than 1 upon 2 raised to power 3 minus 1. 3 minus 1 is 2. So 1 upon 2 raised to power 2. 1 upon 2 raised to power 2. So next we get 1 upon 2 raised to power 3 up to so on, such that 1 upon n factorial is less than 1 upon 2 raised to power n minus 1. Now look at these terms. This is nothing but the geometric series with common difference half, that is 1 by 2. See, first term is 1, second term is 1 by 2, third term is 1 by 2 square. So you can take difference of any two consecutive terms. 1 upon 2 square upon 1 by 2, you will get 1 by 2. 1 by 2 upon 1, you will get 1 by 2. So this is the geometric series with common difference half, and we know the summation formula for this series. Okay, summation formula for the geometric series x is to power n minus 1. Okay, or x is to power n minus 1 is nothing but 1 minus x is to power n upon 1 minus x. This is the sum for first this series, geometric series with common difference. Here was x, here is 1 by 2. Okay, so here we can write this is this less than. Okay, so 1 minus x is to power n. Here x is half, common difference. Okay, so 1 upon 1 by 2 raised to power n upon 1 minus x, that is 1 minus 1 by 2. Okay, this is value of this is, so this is, so our series, this is our SN. Okay, so SN is equal to this. This is our SN. This is less than this term. This term is less than this term. Okay, so we will calculate this. 1 minus 1 by 2 is 1 by 2. So this is equal to 1 minus 1 by 2 raised to power n upon 1 by 2. So something upon 1 by 2. So 1 by 2. So this 2 goes to numerator. So this sequence Sn is less than, this is 2 into 1 minus 1 upon 2 raised to power n. Now, if we put any value of n, so if we put n is equal to 1, so 1 minus 1 by 2 become 1 by 2. 2 into 1 by 2, 1. So less than 2. You go on putting value of n as n tends to infinity. 1 upon 2 raised to power tends to 0. So this tends to 1. So this tends to 2. So this, you put any value, the terms are always less than 2. Okay, because this bracket tending to 1 as n tends to infinity. Okay, so 2 into 1 is 2. So Sn is less than 2. So this implies Sn is always greater than 0 and always less than 2 for all values of n. That is, sequence Sn is bounded. Okay, and here sequence Sn is monotone increasing, and sequence Sn is monotone increasing. Here we have to, it is bounded. So by monotone convergence theorem, the sequence is convergent. Okay, so by monotone convergence theorem, sequence Sn is convergent by monotone convergence theorem. Okay, what we have to, this sequence is monotone increasing and bounded. So by the monotone convergence theorem, this sequence is convergent. Okay.